Maybe I can save this for next year's class. Say hi to your future, the future AP students for next year. Good luck. Don't worry, they all got 5s, definitely. So, okay, so let's go over this one. One of the most famous physics questions. So it's famous because it brings together a lot of things. So first thing, we'll ignore friction because we don't want to make this take all day. If we did friction, this would take a long time because, you know, we have to say friction all the way here or add a part with friction. But let's say no friction for a second. Let's look at the energy at the beginning. We're starting from rest. Everyone, what's our kinetic energy? Good. Our initial kinetic energy, so Ki equals 0. So is that it? Do we have no energy? Good. UGH, also called potential energy. UGH. So initial, which has to do with the weight. Actually, it's good I'm recording for the people absent too, so I can send them. So it's due to the weight, which is mg. Mg is always the weight in this class. So if you see weight, don't forget to multiply by 10, which some of you have already done this year. Multiplied by the height. And we'll do height with respect to the ground, because that's what they showed. Okay, so that's all our energy at the start. We don't have any springs. We don't have any engines. We just want to know if we just let it go, how high does it have to be to complete the whole loop? What you'll find if you do this in practice, that actually just putting it at this height, 2r, is not enough. Even before we get into the math, why might that be the case? What will happen at the top of the loop if you start it here with no friction? It'll go into free fall. So you could describe it many ways. When we say free fall in this class, that actually means a lot of information, but we could actually show from here, it'll continue with initial velocity and it'll kind of go like this. But the important thing, it'll have no normal force, so it won't be able to complete the loop. So we actually needed to have some acceleration at this point in order to get it around there. And as I circled for you, the key equation is the acceleration has to do with the velocity squared of the radius. So when we complete in a loop, we have a minimum velocity having to do with the acceleration and the radius. So we're going to use that in a minute. So we need, for centripetal motion, our velocity squared over the radius to be constant, to keep in that circle. Okay, let's do that diagram for over here. Oops, that's not what I want. Okay, so over here, we're at a lower position, but we're not on the ground. What is our UG final? Nope. Here. Yeah. Here, our UG is actually mg2r. Everyone agree? So we still have potential energy. So UG final is equal to mg, and the height is now 2 times the radius, also known as the diameter, but they showed r, and later it says to solve in terms of r. But is that all the energy we have? No, we just said we need some kinetic energy in order to complete the loop. If we have a velocity of 0 here, no good, all the people are going to fall and die. So we do need some kinetic energy. And we're going to be able to plug in for V in just 1 second. But before we do that, if there's no friction, we can actually use this equation, which is one of our big equations for the unit. If and only if there's no energy, then initial energy is equal to final energy. And these FRQs are going to be tricky, so you really have to go step by step like I just did. Even if I don't ask you to do the energy diagram, on the test I encourage you to do the energy diagram. It'll just help you not make little mistakes with the math. So if and only if there's no work, which is our equation 16b, delta E is 0. So that means the initial energy is equal to the final energy. And this is important because at the beginning, a couple of you are wondering, where's the mass? And as you see, if there's no friction, mass doesn't actually matter. So let me show you why. So our initial energy is just mgh. It was just potential energy, no springs. We're going to be doing that later today. The final potential energy is mg2r, and we're also going to be moving. So this is what you're kind of supposed to, the point that I would have hoped you get to, especially by your test next Friday. Again, you don't need to have figured that all out in your head really quickly, but you do need to get in the practice of doing the energy diagrams, writing everything you know, plugging in, and then you can solve for whatever you want. Now, we know something about that final velocity, that the constant acceleration has to be v squared over r. Can we use that to find what our final velocity will need to be? Any ideas on how to do that? Perfect. Yep. See, she's noticing there's a v squared here and a v squared here, so we can plug in. Everyone see that? This will actually be helpful because then we're getting rid of our v's, which we don't know. We'll put it in terms of acceleration and in terms of the radius. That's good. So let's try that. This would be like the last step of the FRQ. Can I add like background? Oh well, I'll figure that out another time. Put it up here. So mgh. Let me do like a delta potential energy. So I'm gonna rearrange this a little bit. H. We're gonna solve for h later, so never mind. That would be a waste of time. Okay. 1/2 m, and then we're plugging in centripetal acceleration over the radius. So now we got rid of velocity. We have equation without velocity. At this point, I would suggest we also get rid of the masses. So it's just divide everything by mass. GH should be equal to G 2R plus 1/2 centripetal acceleration over the radius. Okay. The last thing that we can do is we actually know something about the centripetal acceleration because we know that it has to do with the weight and the normal force. So I'm going to skip some steps, but at home, you should do the force diagram and see that the centripetal acceleration has to be equal to the weight minus the normal force, because the net force needs to be always towards the center. We're not going to prove that because that was all last unit, and we don't have time to go over that again. But just remember, when we're talking about centripetal acceleration, it's always towards the center if it's constant velocity. So with that in mind, we have GH, and you can go back over this at home again and do the force diagram and prove this to yourself. We'll have 1/2 less U times G over R. Okay, that's just from our force diagram. Again, I'm skipping a couple of steps there, but if you, again, the net force will be down. It'll be mg minus the null force. Okay, now, can we simplify this further? Sure, just divide by g. So actually we get an equation for h. The initial height needs to be minimally, because we're getting this 1/2 a to say the minimum height. We could have a bigger height and then we'll have no problem. But this is the minimum height to do a loop-the-loop. And you can actually demonstrate this if you have like tracks on your own. But it's actually going to be 5/2 times the radius. Kind of interesting. So it's a little bit higher than the initial height, but not much. So you have to have an extra 1/2 r to have enough kinetic energy to complete the loop at a constant velocity. Now in real life, will you get exactly this result? What assumption did we make? No friction. So probably you need to do a little bit higher before you let people get on the roller coaster. Maybe do some margin of error. Don't do the minimum height. Otherwise, one thing goes wrong and everyone goes kaput. Okay, so that's your warm-up. We'll put this on some form of your test next Friday.